Hello everybody, and welcome to page 72 in the workbook. This is the beginning of the Chapter 3 summary, which is kind of a culmination of the main ideas of Chapter 3 in our textbook. Let's talk a minute about the point of this portion of our course. So in Chapter 2, we talked a lot about the idea of the matrix of a linear transformation. And what we're going to do in Chapter 3 is to use that to help us to do calculations involving linear transformations. In a lot of cases, we're interested in finding things like the null space or the range of a linear transformation, or maybe its inverse. And what we're going to see is that having a matrix for a linear transformation gives us a really nice systematic way of finding those things. Okay, so let's start our discussion by looking at this definition here. Part of this is going to be familiar and part of it's going to be new. So we start out with an m by n matrix A and a linear transformation LA that goes from Fn to Fm. Okay, that's just going from the set of all n tuples to m tuples, defined by LA of x equals a times x. We've actually seen this linear transformation before. It's called the left multiplication transformation. We take a vector in x, and to get our output, we just left multiply by the matrix A. Okay, now the next sentence in this definition is going to be new for us. We define the rank of the matrix A to be the rank of the linear transformation LA. Okay, so we already know how to find the rank of a linear transformation. Okay, it's just the dimension of the range. Okay, so what this is saying is that we can also talk about the notion of a rank of a matrix, and we're just going to define that to be the rank of this left multiplication transformation. Okay, now there's one note that kind of goes with this definition. This note is actually a theorem. Okay, and let's read this together. So it says if we start with a linear transformation T from V to W, okay, where V and W are both finite dimensional vector spaces, and if we choose a basis, beta and gamma, for our domain V and our codomain W, then the rank of that linear transformation will actually equal the rank of the matrix of that transformation taking us from beta to gamma coordinates. Okay, so it's just saying that if you have a linear transformation like this and you choose bases for the domain and the codomain, then the rank of that transformation will always match the rank of the matrix of the transformation, whatever those bases are that you choose. Okay, now let's do one example together here. Okay, this is the first example of helping us to kind of get to know these left multiplication transformations a little bit better. We'll be using those a lot in this Chapter 3 summary. Okay, so it would like us to describe the range and the null space of L of A for this 3 by 3 matrix that they're giving us. Okay, so let's start out by making an observation here. So we will note that if we look at AX, okay, that's kind of intimately related to this left multiplication operator. We want to just take a look at that expression. So A times X would look like the matrix that they gave us times a vector. Okay, and so that the dimensions work out, that vector is going to be a 3 by 1. So we'll label it x1, x2, x3. And I want to just play with that expression and see what that really looks like. So if we do this matrix multiplication, take the first row and multiply that through, we're going to get 1x1 plus 0x2. Actually, I could not write that. I'm going to go ahead and write it out anyway, though. 0x2 plus 1x3. Okay, and then the second row we'd get minus 1x1 plus 1x2 plus 0x3, and then the third row, same idea. Okay, we're just using ordinary matrix multiplication there. All right, I want to rewrite this one more time. Okay, we can kind of break this down kind of component by component relative to the vector that we multiplied by. So for example, I'm going to start this off by writing x1 times 1, negative 1, 2. Now, where did that vector come from? Notice that the 1, negative 1, 2 came from these coefficients. Okay, and then we'll add that to the piece that kind of goes with x2 times 0, 1, 3. Okay, and again, the 0, 1, 3 are coming from here. Okay, and then one more time to get the x3s in there, x3 times 1, 0, 5. Okay, and if you kind of do the calculation in the reverse order and take what we just wrote and add all of that together, you'll notice that it does simplify to what we had above. So those really are equal to each other. Okay, but what's interesting about this way of rewriting this is where these three vectors come from. Notice that those three vectors are exactly the columns in the matrix that we started with. Okay, so this is telling us that we can kind of think of A times X as just being a linear combination of the columns in our matrix A. That will always happen. All right, so what can we take from this? Well, that means then that the range of L of A, okay, which, just to refresh your memory, is the set of all things that look like A times X, okay, will be the span of the columns of our matrix. That's what our calculation above tells us. Okay, and then what about the null space of L of A? Okay, well, the null space of a linear transformation is the set of all inputs, which in this case would be x, such that the output is equal to 0, and the output of this transformation is ax. Okay, so it's the set of all inputs such that ax equals 0, but what's interesting about that is that ax equals 0 vector, that's actually a system of equations, if you think about it. And so one way to describe the null space of L of A is the set of all solutions to the system of equations that looks like ax equals 0. Okay, so this example that we just did gives us kind of a quick, convenient description of the range and the null space of a left multiplication operator. These general observations are things that we're going to use for the remainder of this chapter summary.